Oh, I yeah, I thought you I'm taking you home. I didn't say co-workers or yeah, because like someone was all shared that yeah, it was shared that they don't make it. Good, how are you? That part I'm not sure. Yeah. And they have an Xbox. They play on my TV. A lot of people getting really
Okay, let's get started now that the silly camera is working. Some days it takes rebooting the camera, some days it takes just switching to camera mode and switching back, and anyway. So how's it going? Got the lab done? Due tonight, right? Now that I got your attention. There's some not so fun stuff about Lab 6. Let me rephrase it. There's some really fun stuff about Lab 6. We'll put it that way. And the really fun stuff about Lab 6 isn't the first phase. That's mostly fun. There's a big difference between mostly fun and all fun. With all fun, there's only one thing you can do. So the all fun part about Lab 6 is the optimization part, where you're supposed to optimize the context switch so that you don't push the state twice. The problem is that if you've got context switch code, and that context switch code is designed to be used with both preemptive and cooperative context switching, and you've got the ISR's code, well, if you just remove the STMFD and the LDMFD from the context switch code and just say, well, I'm just going to rely on the ISRs to save my state, what happens if you cooperatively swap yourself out? So on a preemptive swap out, you end up saving state twice. On a cooperative swap out, you save state once. If you remove the state saving from the context switch, on a cooperative swap out, you end up saving state 0 times. I hope you will agree with me that that's bad. If you don't, we need to talk. Okay? But, so, then we could perhaps target the code that you save the state inside the interrupt, and don't save the state when you interrupt the program in order to keep from saving state twice. Well, if you do that, then what happens if a program that gets running runs an interrupt that does not lead to a context switch? You interrupt your program, you go and you handle the interrupt by running your handler, and you mess up all the registers inside your handler, and then you go back to run your program, and all of a sudden your program doesn't run correctly anymore because you didn't save the state inside the interrupt. So when you interrupt the program, you have to save state. When you swap a process out, you have to save state. And yet we save state twice. So how do we get around saving state twice? when you're preemptively swapping out a program. Here is the hint that I will give you. Think really hard. No. You know how to make decisions inside your programs that you're running. If you remember information at appropriate locations, you can determine whether or not the process that you're swapping out is being swapped out preemptively. You know how to query state information, and there's nothing saying you can't alter the type of information you keep track of, i.e. the process data structure. There's nothing saying you can't fiddle around with the process data structure or other locations. Don't do this in a global variable. You want, if you're trying to keep track of state information associated with a process, keep track of it in the process data structure. But you can remember how a process gets swapped out. You can remember how you are swapping out a process, and you can remember how the process that you're swapping in was swapped out. How do you remember that? Well, you create a variable and you write a value to that variable that indicates how was this process swapped out, or how is this process being swapped out. And then you could have multiple implementations of a context switch that does the right thing for swapping in and swapping out processes that have been swapped in and swapped out differently. Okay, there you go. I've said too much. If statements are your friends, it might require a little bit of assembly coding. Just a little bit. Just a touch. Yep. Okay, yes.
So, we have the two set of code, right? The IRS.s.
ISRs.s and CS.s, yes.
Okay. How can we go about finding out when CS.s is called?
How can you find?
When is that called?
Okay, so the control flow, when CS gets called, it can be called in one of two ways. The process code that you're running, if it calls schedule next process may end up calling context switch. The reason why it may end up calling context switch is because if you have a process to switch to under Lab 6, if there's a process in the ready queue, it'll switch. Okay. So if you just say that I've got 3 processes and they're all ready, and I've got one process that's running, that means you've got a total of 4 processes, 3 of them on the ready queue. If you call schedule next process, whether from an interrupt or from a process, it'll switch. It'll call a context switch. Okay? So your process never calls context switch. Your process calls the scheduler. And PIT never calls context switch. PIT calls the scheduler. Okay? So you're going to have a call to schedule next process in potentially one of 2 different places. One directly inside your process. Another one inside a call to PIT. Okay? And both of those could lead to a context switch.
But the scheduler is the one who actually does the calling.
Yeah, the scheduler is schedule next process. It's the function that I wrote on the board or put in the notes, schedule next process. That's the scheduler. It is responsible for calling context switch, and nowhere else do you call context switch except for from schedule next process and from start scheduler. Okay? So the question isn't, where does CS get called? The question is, where does the scheduler get called? A way of testing this, you're going to have to, so what I've done is I've shown you a block of code where you have a whole bunch of, you can create a bunch of processes that all share the same code. I would suggest that you use that as testing for your implementation, but that you also create another framework where you have one process and you have different blocks of code for each of your processes. And you have it distinguish itself based on the different processes. The reason why is because if you're monkeying around with a state that gets saved, and the parameter that you're saving, that you're printing out inside the process, the only way to distinguish what one process is from another is the value that it prints to the screen. It accesses the value that it prints to the screen by accessing a value passed to it in a register. If you're not saving and restoring the registers correctly, that value is going to get messed up. Okay? And you won't be able to tell which process is actually running based on the parameter that you're printing, because you can't attribute it to, well, this is the process that's running, or my parameters messed up because I pushed and popped the registers wrong. So write out different process implementations for each of your processes for one test that you're doing. Okay? Does that make sense? All right. Other questions about Lab 6? Draw your stack frame first. That's why it's the first phase. That really helps. Okay. Semaphores, Lab 7 stuff. So we're going to finish, I'm going to just briefly go over again the weak semaphores, and then we'll dive into the strong semaphores, and then we'll talk about the bounded buffer problem. Okay. So if you remember, we talked about weak semaphores. We gave a definition of weak semaphores. The whole point of a semaphore is to protect the critical region, to provide mutual exclusion under the assumption that those processes which are accessing a critical region properly invoke the semaphore code so that the semaphores can do their job to protect the access to the critical region. Okay? So every process that shares a critical region will share a semaphore, and every process that wants to enter the critical region has to access the P version of that semaphore. So if it's a weak semaphore, we're going to access weak P. And we pass to weak P the semaphore that we're sharing. So it's not that you just call weak P before you go into a critical section. You call weak P and you pass a shared semaphore. All the processes that share a critical section have to share the same semaphore to protect that critical region. If you have different semaphores for different processes, but a shared critical region, you're not going to protect the critical region by having each of them access a different semaphore. Okay, so weak P has a for loop where you loop forever, you disable the interrupt, you query the semaphore's count, you decrement the count, enable the interrupt, and return under the assumption that the count is indicating that the semaphore is available. If the semaphore is not available, somebody else owns it, so we just swap ourselves out and let somebody else run under the assumption that they're eventually going to run and give up the semaphore, and maybe I'll be able to get it. This does not guarantee that I get it. I'm just hoping that somebody else will give it up and not want it again, and eventually when I get swapped back in, it'll allow me to grab it. And that is the problem with the weak semaphores, because I'm just hoping that somebody else will let me have access to it. Okay? The way the strong semaphore fixes that is it guarantees that as soon as I notice that I can't have a semaphore, I get put onto a list, a queue, waiting for that semaphore. And when we're doing fair scheduling, then that semaphore is granted to whoever's been waiting for it the longest, before it's just made generally available. Okay, here we have no notion of who's waiting for it. All that we have is it's available or it's not available. And if it's not available, everybody's got to wait who wants it. So the problem with a weak semaphore is you can starve a process unintentionally. So we go over to the strong semaphore implementation. So we said with a strong semaphore implementation, we've got a FIFO inside our strong semaphore. That's our blocked queue and a count. Okay, this count is the same count as the weak semaphore. It just says, is the semaphore available, yes or no, or how many slots in the semaphore are available. It's a counting semaphore. We've got this blocked queue here. That blocked queue, what it does is it says, who's waiting for this semaphore? Okay? And if somebody has attempted to do a P on a semaphore that isn't available, they get queued up into the blocked queue of the semaphore. Again, this is not like your ready queue, which is a global structure. Each individual strong semaphore has its own blocked queue. You don't wait on a global, I'm waiting for a semaphore. You have a blocked queue for the semaphore so that you're waiting for that semaphore. Okay? And so you can only be on a single blocked queue at a time, simply because when you try to access a semaphore, if you get on its blocked queue, you're not allowed to go and execute another instruction which will allow you to go and attempt to grab another semaphore. So you can only be on a blocked queue, a ready queue, or you can be the running process. You can't be on more than one processes or more than one semaphore's blocked queue. 3 functions, strong P, strong V, and strong init. Don't pass a weak semaphore to strong P. It no worky. Compiler will yell at you. You could attempt to make it work by casting a pointer to be of the right type, and then you'd really be in trouble. You know, of all the various errors that I've seen people do, I don't think I've ever actually seen somebody try to do that. It'll be an adventure to see what would happen. Anyway, we got two helper functions, move to blocked queue, and then move blocked to ready. The strong P implementation here disables the interrupt. So when this gets called, that means a process is attempting to enter a critical region protected by a strong semaphore pointed to by S. We check S's count to see if the semaphore is available. If it's not available, then we block. If it is available, we decrement the count, enable the interrupt, and return. The moment that we return, that means we own the semaphore and we are able to go and access the critical region. Okay? So move to block queue, what this does, this is kind of funny because we just have this function that we call move to block queue. So if the semaphore is not available, we move the process that's currently running, that's the process that called strong P, we move him to the block queue and we pass S because we're putting him on the block queue of the strong semaphore S. Then what happens? After we move the process to the block queue, we enable the interrupt and then we return from strong P, allowing the process to access the critical region. Does that seem kind of funny to anybody? You block the process, then you go and you access the critical region. The whole point about blocking the process is to keep it from accessing the critical region. We don't want it to access the critical region until it owns the semaphore. Okay? But yet this seems kind of counterintuitive because we block the process, and as soon as control returns from here, we allow it to go and access the critical region. So the question then becomes, is that protecting the critical region? What gives here? Why do we allow control to return from move to block queue and go straight to the enable, straight off into the implementation? Why is that safe, good, okay, life's happy?
Strong V. Actually get in wherever you're trying to get in.
Strong V, get into wherever you're trying to get in. Nope, that's not what's going on. What is the control flow that has to happen to move to blocked queue? What does it mean if you're going to block a process? Remember how I told you the process lifetime is you can be ready, running, or blocked? Is a blocked process running? No. So if you're moving a process to a blocked queue, that means you're blocking a process. That means it's not going to run. So what does this statement imply? It means I'm going to swap it out. Now, so I am going to context switch. This guy has got to call context switch. He's got to swap the process that's currently running out. Why? Because he's not ready anymore. He's not running anymore. I've got to prevent him from running. Why am I trying to prevent him from running? Yeah, he's trying to go where he can't go. I'm not allowing. He's got a big red light. Okay? When do I give him a green light? He can only go again when he owns the semaphore. Okay, so I swap him out until he gets ownership of the semaphore.
So a process gets swapped in, call strong P. It moves to the block queue and gets swapped out. Is it even going to return to here?
Okay, so that's a good question of when a process runs, eventually we'll access strong P, let's suppose, and let's suppose the semaphore is not available. I'm repeating what you just said so the distance guys can understand. And then, so you call strong P on an unavailable semaphore, you get put on the block queue. Now the question is, will you ever return from being blocked? Or when do you return from being blocked?
I'm just wondering if you come back to this process.
Do you come back to this process?
So you get swapped out in the middle of this.
Okay, so do you ever come back to this process? So first principle is, whenever you swap a process out, it's like you're freezing it. When you swap it back in, you'll resume exactly where you left off. Okay? So that's the principle here. We got a massage into the head here. Whenever you swap a process out, all that you're doing is you're pushing the stop button on it. And as soon as you hit the play button again, it'll go right back where it was. Okay? So we're going to have control flow go from move to block queue through a context switch. That'll freeze the calling process. Now the question is, when does it get unfrozen? It will not be unfrozen until we can swap it back in, or until we're allowing it to run. And we're not going to allow it to not be blocked anymore until it owns the semaphore. Okay? So we have to structure this code such that the process that is on the block queue does not get moved back to the ready queue until that process is granted ownership of the semaphore. Okay, does that make sense? And when we grant it ownership of the semaphore, eventually it'll get swapped back in. So granting it ownership of the semaphore moves us from the block queue to the ready queue. Control flow for the process that calls this still hasn't moved yet. It won't move again until that process becomes the running process. So we move the running process to the block queue. We shuffle the pointer to that process around later on, and eventually it'll get swapped back in only after it's granted ownership of the semaphore. When it's granted ownership of the semaphore, it's moved to the ready queue. It sits on the ready queue till it gets swapped in. When it gets swapped in, then control resumes from the point where this process was when it got blocked. So what will happen here is it'll get swapped in, and it'll return from the CS call that caused it to get swapped out. And then control flow will resume right back here. That function call return will exit strong P under owning the semaphore. Okay? So move to block queue is enough to say, okay, throw this guy out, block him. This function will not return until A, the calling process owns the semaphore. B, the calling process has been moved off of the semaphore's block queue onto the ready queue. C, the scheduler has decided to move that process from the ready queue to be the running process. And D, has swapped it in. Okay? As soon as that happens, then it's okay for control to return from strong P for that process. Okay? Remember how I said control flow can change in non-obvious ways, and that's why we use volatile keywords and things like that? This is why. Because you've got funky things going on under the hood. And the code doesn't look like it does what it's supposed to do, but it does. So now the next question is, what causes a process to get moved off of a blocked queue? And that's the code that we had in strong V. Who calls strong V? So let's suppose that we have a process that runs, process A. It runs, it grabs a strong semaphore, and it enters the critical region, and then you get an interrupt, and it gets preempted while it owns the semaphore. Process B runs. Let's suppose process B runs for a bit and tries to grab the semaphore. The semaphore is not available, so it gets blocked. Now let's suppose we run process C. Process C, it can run for a while. Let's suppose it doesn't want that semaphore, and it'll just run for a while, and then eventually it'll get preempted and swapped back out. And let's suppose we now go back to process A. Process A runs. Process A completes its duties inside the critical region, and now it wants to give up the semaphore. How does it give up the semaphore? It calls strong V. And again, this whole time, you can have other processes that run that don't want the semaphore, but only one process is allowed to own the semaphore at a time under the assumption that the count for that strong semaphore is initialized to 1. Okay, so the owning process calls strong V. Recall that the process that wants the semaphore, process B, has already been through strong P, has gone to move to block Q, and he's stuck. He's swapped out on the block queue. He can't return from this location until some other process called strong V. This other process, process A, is done with a semaphore, called strong V. That causes us to disable the interrupt. Now what we do is we check the semaphore's block queue. Process B is on the block queue. So if the FIFO count of the block queue is greater than 0, that means there's a process that's blocked that's waiting for this semaphore. What we're going to do, instead of incrementing the semaphore's count and saying that it's available, and then checking to see if somebody wants the semaphore, what we're going to do is just pretend like we plus the count and then minus the count altogether, which does nothing. So we're going to leave the count at 0 and just grant ownership implicitly to the process that's blocked. How do we grant ownership? Well, we're going to move that process that's blocked to the ready queue. That process is this process B that's stuck over here inside moved block queue waiting for somebody to swap it back in. Okay? So we move blocked to ready. So what that does is it accesses the block queue for the strong semaphore. And it grabs the process off of that and it inserts it into the ready queue, the global ready queue. It doesn't necessarily switch to that process it just put onto the ready queue. It just puts it into the ready queue. Okay? So the other thing that it can do, and you've got to decide whether or not this is appropriate, it can call a scheduler. So it's up to the scheduler to decide who should run when. So you make that process that you're unblocking available to the scheduler to pick. But you don't say you have to pick this one. What you do is you give it to the scheduler, and the scheduler then gets to decide who gets to run. So if you call the scheduler, maybe the scheduler will decide that the process who called strong V gets to keep running. Or maybe the scheduler will decide the process you just swapped in gets to run. Or not the process you swapped in, the process you moved from blocked to ready. But nevertheless, you give that option to the scheduler by calling the scheduler after you've moved that process that was blocked onto the ready queue. Then you enable the interrupt and return. So this, again, is the process that called strong V that had formerly owned the semaphore. So as soon as it moved the blocked process to the ready queue, that does not block the calling process. That doesn't impact the calling process. All that it does is it just moves the process that was blocked to the ready queue. He gets the semaphore. We enable the interrupt and return. Okay. Otherwise, if there's no process that's blocked, we just increment the semaphore's count, enable the interrupt, and return. Okay? So the only time we increment the semaphore's count is if nobody wants the semaphore, if nobody's currently waiting for the semaphore. So what this does is it just does this implicit move that if somebody's waiting for it, they get it. It prevents me from going and asking for the semaphore again before that process has a chance to ask for it again. And that's why this guy prevents starvation. Okay. So, is this stuff clear as mud? Strong semaphores? Yeah, Derek.
When you say two blocks ready, does that pull it off the block queue and puts it in the ready queue?
Okay, so it pulls it off the block queue and puts it into the ready queue. Yes, you are right, but I want you to clarify who is it. Which process? There's two processes here. There's a process that's blocked, and there's a process that's called strong V, and they're not the same thing. Who's on the block queue? Process A is not on the process A. I forgot who I said. Process A is not the guy that was blocked. It was B that was blocked. B calls strong. A calls strong V. B's blocked.
So B is blocked, and then so the blocked ready is going to take B off the block queue and move it to the ready queue.
Yes. So by A calling strong V, it moves B off of the semaphore's block queue and moves it onto the ready queue. So let me tell you this much. At that point, is A on the ready queue? What is A doing? A is not dying. A is the running process. So now let me ask you, is the running process on the ready queue or not? Maybe. Maybe not. There are multiple ways of doing it, and you can do both ways correctly. Okay? Just because it's on the ready queue does not necessarily mean it's ready. There may be a time, especially if we get to table-based scheduling in Lab 8, where you're going to want to make the running process be on the ready queue. And it particularly makes the implementation of PCP semaphores that we'll talk about in Chapter 13 much better. Oh, you see?
So the process so when it calls
when it calls strong V.
Yeah, when it calls strong V, that doesn't mean the process is done. It just means it's done with critical section.
That's just saying, so when process A calls strong V, he's not yielding the processor necessarily. He's just saying, I'm done with my critical region. I'm giving up the semaphore. Okay. So, yep.
There are several semaphores. They each have a block queue and
Mm-hmm.
okay, never mind.
Okay.
The semaphore has the queue and like inside the semaphore.
Yes. Multiple semaphores. You have multiple block queues. A process would reside on the semaphore's block queue that it wants. Okay. So, the scenario before that we were showing where you've got two processes that are running. So you process P1 does a strong P on a semaphore that's protecting the critical region. The critical region is printf. We're trying to print to the screen. There's only one serial port, so we have to protect it with a semaphore. So strong P on that semaphore. We start to print. Let's suppose in the middle of the print we get interrupted. We swap over to process P2. P2 does a strong P on the semaphore S. The semaphore is not available because P1 owns it. So P2 gets put on S's blocked queue. Okay? Because it gets put on S's blocked queue, it can't run anymore. So we've got to call the scheduler to run whichever process is ready. So because we only have two processes, P1 is ready, nothing else is ready, so we swap back to P1. So when we swap back to P1, P1 resumes doing whatever it was doing before it got swapped out. It finishes printing. It releases the semaphore. When it releases the semaphore, that implicitly gives the semaphore to P2, and it causes P2 to be moved from S's blocked queue to the ready queue. Okay? So P1 does a strong V on S. That causes P2 to be available to execute. And then let's suppose that P1 continues to run, and then it calls strong P on the semaphore S. This is what got us into trouble with a weak semaphore. But now, because of the fact we have the block queue, and we passed ownership of the semaphore with the call to strong V from P1, we passed ownership to P2. When P1 calls strong P on the semaphore again, it queries the count and it says, oh, this semaphore is not available. So now P1 goes onto the block queue of the semaphore. And because it goes onto the block queue of the semaphore, we have to swap him out. We swap him out, we go over and we now allow P2 to run. P2 now is able to do its critical section. So it does its print, even if it gets preempted in the middle or even if it gets an interrupt in the middle. The schedule will be called and it'll notice that there's no other processes to run, so we'll keep running P2. The reason why no other process is able to run is because P1's on the block queue, the ready queue is empty, the running process is P2, so there's nobody else to run. So it can't really get preempted just because there's no other processes to run. So P2 is able to finish its critical section. It does a strong V. When it does a strong V, it says, there's somebody waiting on the block queue. That process that's waiting is P1. And that grants ownership of the semaphore over to P1. P2 continues to run until it attempts to grab the semaphore again. When it attempts to grab the semaphore again, it gets blocked, and we just swap back and forth in this fashion. So what this does is it allows the strong semaphore to guarantee mutual exclusion on the critical region, and it also avoids the unintentional starvation of a process. Okay? And again, let me emphasize on that word that I said, unintentional. There are times and situations where we intend to starve a process, and we want to starve a process. Okay? Starvation of a process is not necessarily an evil topic unless you don't intend to do it. The problem that I get into is, so the next topic we're talking about is priority scheduling. And the problem that we get into with priority scheduling, where everybody gets mixed up, is with priority scheduling, you are being biased. You are being unfair. You are dictating that if a high priority process wants the CPU, they get it. If a low priority process wants the CPU at the same time that a high priority process wants the CPU, guess what? Mr. Piggy high priority process wins. If the high priority process always wants the CPU, they always get it. That leads to starvation of the low priority process. And that's correct. Okay? So we want to avoid starvation in those situations where we intentionally have fair processing. So Lab 6 is focusing on fair scheduling, round-robin scheduling. Lab 7, we are doing priority scheduling. How do we do priority scheduling? We're going to assign a priority to each process. The priority is a non-negative integer. We're going to assign priority in this order. The book decides that they like priorities being assigned in the opposite order. They're wrong. I'm right. Good to be the king. Okay, so 0 is the highest priority. 63 is the lowest priority. Okay? Tasks cannot share priority. So there is no such thing as a task being of equal priority as another task. Okay? So the goal of your scheduler, instead of let everybody run an equal amount of time, your goal of your scheduler now is run the highest priority process that's ready. Okay? So if you have the highest priority process that wants the CPU, they get it. And they get it as much as they get the CPU for as much as they want until they don't want the CPU anymore. What do I mean by want the CPU? Well, if the highest priority process is ready, it gets to run. Every time the scheduler runs, it just says, whoever is on my ready queue, the highest priority one of those processes, they get to have the CPU. If that process is the one that's currently running, great, we'll just let them run. How can a process not want the CPU? Well, a process may want a CPU, but it can't have the CPU when it's blocked. Okay, so if a process is waiting on a semaphore, and it's in the block queue of a semaphore, it can't get access to the CPU. So if the highest priority process attempts to grab a semaphore that's owned by somebody else, then it has to wait. It goes to that process or that semaphore's block queue and sits there until the semaphore becomes available. As soon as that semaphore becomes available, then the high priority process grabs it and it is able to run. Okay. So, again, don't get confused. Lab 6 is fair scheduling. Lab 7 is priority scheduling. You have to, in Lab 7, modify your scheduler that's currently doing fair scheduling to do priority scheduling. If you implement your scheduler correctly in Lab 6, this change is fairly painless. Okay? The reason why is because all you have to do is modify the implementation of your priority, or the implementation of your FIFO to be a priority queue instead of a regular FIFO. And if you have set up your interface correctly, then your scheduler code doesn't have to change. Just your implementation. Now, you might want to not turn your brain off, and you might want to make sure that everything's okay, because I'm sure you don't have a whole lot of experience building strong interfaces that you don't have to change. But just be careful on what you're doing, on how you're implementing your interface, how you're implementing your module. And if you do this correctly, when you go to implement your priority queue, you shouldn't have to change a whole lot of code and everywhere else inside your Lab 6 code base when you're doing Lab 7. Okay, so in order to do this, you're going to have to take your FIFO from Lab 0, and you're going to have to modify it to be a priority queue. Okay, you can implement your priority queue in one of two ways. You can either, as you're inserting tasks into the priority queue, you can sort them as you add them. Or alternatively, you can, whenever you want to remove a task or query the priority queue to figure out what's the highest priority task in there, you can search the queue for the highest priority on removal. Okay? You don't do them both. You do one or the other. So you either sort them as you insert them. So what that means is on insertion, you find the right spot inside your linked list of where to put this task. So you're maintaining a sorted linked list. Or alternatively, you maintain an unsorted linked list that's just in there perhaps in FIFO order. When you remove, what you have to do is loop through all the elements in the list and figure out which one is the highest priority element, and you remove the highest priority element. So either way, which one's more efficient? Well, that depends on what you're doing more frequently. If you query more often than you swap. So if you're going to ask your priority queue, what's the highest priority process? And if you ask it that question more often than you actually remove something, then the first point is much more efficient, because when you maintain a priority queue in sorted priority order, checking it for the highest priority is order 1. Insertion is order n. When you maintain an unsorted list and you want to do a check or an insertion, checking is order n, insertion is order 1. So the penalty that you pay is right here, because we check much more frequently than we insert. Okay, the reason why is because of this notion that when you call your priority queue, you're going to check to see if the currently running process has a lower priority than somebody on your priority queue. And very frequently, the process that's running is the highest priority process. So you're going to be, every time you get a timer interrupt, checking your priority queue and realizing that I don't need to swap. So you check and you don't swap. In the worst case, you'll check and swap every time. So it just becomes, so insertion on that case becomes order 1. Removal, when you're maintaining an unsorted list, basically same thing, order n. Removal when you're doing an unsorted list is order n. Removal when you're maintaining a sorted list is order 1. Okay. So you modify your FIFO to implement a priority queue. Respect to your modularity. Well, here's the other thing, is when you are doing priority queues, your ready queue, when you're doing priority scheduling, your ready queue needs to be a priority queue. The block queue in your semaphores need to be a priority queue. So what this means is that if you have two processes that both have attempted to access a semaphore that's not available, the semaphore, when it becomes available, is granted to the process that has higher priority, not the process that's been waiting the longest. Okay? So semaphores are granted in priority order, and access to the CPU is granted in priority order. Okay? So Now basically you have all the stuff you need to do in order to do Lab 7.
That's great.
Yeah.
So if you make the block queue a priority queue, assuming that the priority is not going to change.
Yeah, we don't change priorities of processes necessarily.
So
There are situations and times where you might want to, when we get into Chapter 13, we will mandate that we have fixed priority scheduling so that you cannot change the priority of a process. But then we'll undo that with priority inversion and all that. Anyway.
So won't we have the same issues with starvation that's connected to that thing then?
So the question is, if we have priorities and our block queues are priority queues, won't we have issues with starvation? Yes, we will. This is the whole intentional versus unintentional issue. So because of the fact that we declare we are a priority scheduler, we're saying it's more important that we meet the priority rules of the processes than it is that we don't allow starvation. So we intentionally starve processes. Low priority processes intentionally get starved if higher priority processes want the CPU.
So what if we just want to do printf into different processes and we actually want them to be of equal priority?
So if you want to do printf in two processes and you want them to be equal priority, what you're going to end up doing is a technique that's similar to the last phase of Lab 7, which asks you to use a priority scheduler but make it look like it's doing fair scheduling, which is the gotcha part of Lab 7. So good question, Mitch. So yes, you're going to have to do that. And no, I'm not going to tell you how. You're going to tell me how. Okay? Other questions? Okay, we're going to look at bounded buffer and a semaphore example next, which is bounded buffer. Okay. Blackout. Here we go. Here's the quote of the day. Semaphores make my head hurt. Well, try not using them. Then we'll see how bad your head hurts. So, bounded buffer problem. Whenever you talk about operating systems in computer science classes, not to diss too much on computer science classes, but when you're worried about the abstraction, you're not worried about the implementation. Oftentimes when they talk about semaphores, they teach you the dining philosopher's problem and the bounded buffer problem and, various other classical computer science problems that are very theoretical in nature, okay? And you never see how a semaphore is implemented. And, a computer science guy feels dirty if you ever talk about disabling the interrupt to prevent a process from getting preempted. So that's just not theoretically nice. It's just, what are you talking about the implementation details for? With our approach is we are looking specifically at the implementation details, and we're a little bit lighter on the theory part of semaphores. Okay, but I do want you to see one of the classical problems in computer science, a semaphore-oriented problem, and I want you to be able to think about how to use semaphores to protect critical regions. So what we're going to do, this is a classical problem called the bounded buffer problem. We have a buffer that's of finite length, and it has slots in it, and you're going to put data into the slots, and you're going to remove data from the slots. So the whole idea is we're going to have one process that's in charge of producing data and putting data into the buffer, another process that's in charge of removing data from the buffer. So the whole idea is we want to make sure that the inserting process doesn't mess up the removing process, and that the removing process doesn't mess up the inserting process, and so forth. Okay, so we call the guy who inserts the producer. We call the guy that removes the consumer. Okay? All interactions between the producer and the consumer, they interact in units of one data. So when the producer produces data, it's one slot in the bounded buffer. When the consumer consumes, he takes one slot from the bounded buffer. Okay? The rules that we want to enforce with the bounded buffer problem. Number one, we want to make sure that we never insert into a full buffer. Number two, we want to make sure that we never remove from an empty buffer. Number three, we want to make sure we never remove while we're in the middle of an insertion operation. Number four, we want to make sure that we never insert while we're in the middle of a remove operation. Okay? The reason why is because the internal state of the buffer is going to get messed up. So we have to maintain a pointer to wherever we're inserting and a pointer to wherever we're removing and keep a count of how many slots are in there. And really in C, the implementation of the bounded buffer is going to be something like a circular buffer where you're going to fill up a bunch of slots, then carriage return and fill up a bunch of slots. So sometimes your read and write pointers will look like this, sometimes they'll be like this, and it's easy to mess it up. So we want to make sure that we don't corrupt the internal state of the bounded buffer by having concurrent accesses to shared variables. We've seen what happens when you have concurrent accesses to I++. Okay, so the whole idea is producers in a thread, consumers in a different thread. The bounded buffer is a shared data structure between them. So let's suppose that we have something like this. For doing insertion, this is what the algorithm for the producer could look like. We have a while loop, say while 1, if buffer size greater than max, so let's suppose the buffer size is some global variable, and the buffer size is a variable that indicates how many slots are available in the buffer. So if the buffer size is greater than max, we sleep, and then we continue. So what this is doing is it's trying to keep us from inserting into a full buffer. So if the number of tokens in the buffer is greater than the number of slots available, then we have to wait until the consumer consumes the token. So if buffer size is greater than max, yield the processor, and then continue. Check again. Okay? As soon as buffer size is not greater than max, we insert an item, and then we increment buffer size and we return. Okay? Consumer, similarly, it's going to enter a while loop that says if buffer size less than 0, we'll sleep and continue. So this is just going to wait until there's data in the buffer to consume. So if there's no data available, I wait until a producer produces a token into the buffer. Otherwise I'm going to consume from an empty buffer. So I will make sure that I don't consume from an empty buffer. As soon as the buffer has data into it, I'm going to call remove. I'm going to remove that data item and put it into the variable item. I'll decrement the buffer size and return item. You like that implementation? Does it work? Does it satisfy the criteria that we've specified? Does it keep the producer thread and the consumer thread from violating any of those rules? Yeah, why would we be talking about this if there's no semaphores? Come on. Okay, so both threads can access the variable buffer size. And if you remember, we're doing plus plus on buffer size and minus minus on buffer size. Both the threads can simultaneously access that global variable. And we've already talked about how I++ is bad when you have, and it can lead to race conditions or can lead to two pluses end up incrementing by 1 instead of by 2. So buff size is a critical region. Buff itself is a critical region. So every time we're accessing buff here, inside the consumer and inside the producer, that's accessing internal state of a data structure. Buffer size is a variable that's being shared by these two threads. We have to protect those. So what we're going to do is we're going to define two counting semaphores, full count and empty count. What the producer is going to do, and so we're going to initialize, we're going to initialize full count to 0 and empty count to max. So what we're keeping track of is how many tokens are in the buffer and how many available slots are in the buffer. So what the producer is going to do is he'll do a P on empty count. So he'll say, is there a slot available for me to put something in? We initialize empty count to max. So what that'll do is it'll allow this P to succeed up until we don't have any tokens left in the buffer. So we'll do a P on empty count. So that means there is a slot available. We'll insert item into the buffer. Then we'll do a V on full count. So what that does is it decrements our count. So effectively, we're merging the idea of a semaphore and a counter by using counting semaphores here. Doing a V on full count, that says the number of items in the buffer has gone up by 1. When we do a P on empty count, that decreases or decrements the number of slots available in the buffer. What the consumer then does, it does similar, but it does the opposite order. There's a P on full count. What that does is it accesses how many items are in the buffer. Is there an item available? If there is, I say item equals buff.remove. Syntax is a little messed up there. Then I do a V on empty count. So when by removing an item from there, I decrement I do an increment on the empty count, which says there's now one more slot available. Okay, you happy with that? Critical region protected. Rules 1 and 2. Is there any way for the producer to produce into a full buffer As soon as the buffer is full, empty count will be 0. That semaphore will not be available, and this guy has to wait, and he'll be blocked. Okay? Likewise with a consumer, can a consumer remove from an empty buffer? As soon as he does a P on full count, if the buffer is empty, full count will be 0, and the consumer will have to wait. Okay? So this does protect against rule number 1 and rule number 2. We make sure that we can't insert into a full buffer and we can't remove from an empty buffer. Does it make sure that we can't produce while we're consuming and consume while we're producing? Does this protect against concurrent access to buff? So what this allows us, it allows the producer to get in an access buff, but there's nothing saying you can't be in the middle of an access to buff, preempt, come over here, and have a consumer run and get in the middle of an access to buff at the same time. The reason why is because we allow the producer to keep producing while there's slots available, and we allow the consumer to keep consuming while there's data tokens available. So we need to add one more thing in order to protect against rules 3 and 4. So what we do is we have a semaphore called buff lock. So every time we access buff, we're going to protect the access to buff with the semaphore that's a binary semaphore. So we do a P on buff lock before we access buff, and then we do a V on buff lock. Similarly, in the consumer, we do a P on buff lock and a V on buff lock surrounding the access to buff. Okay? So semaphores are used to access and protect critical regions. Make sure you are aware of what your critical regions are. Okay, thank you.
So